Good morning. In this class, we will cover simplest radical form. First, a radical is comprised of the index n and the radicand a. So that refers to this notation here. When we are writing our radical in simplest form, there are three things that we must check. So first, we're going to remove all perfect nth power factors from a radical of index n. So what does this mean? If it is a square root, we will check for any perfect square factors because this will allow us to reduce the radical. And we'll look at many examples of this. Sometimes it'll be possible to reduce the actual index. Okay, and again, I will show you examples of this. And lastly, if there is a denominator, we want to make sure there are no radicals left in the denominator. So we rationalize the denominator. Okay, so by way of explanation of these rules, I'm going to go through the even numbered problems from your textbook. These are exercises 11.3. So here's our first example. We have the square root of 216. So again, if there is no index written here, it's implied to be 2. So we are looking for any powers of 2 that divide evenly into 216. Okay, so perfect square factors. So this means check for 2 squared, 3 squared, 4 squared, 5 squared, etc. So we're checking for 4 and 9, 16, 25, and so on. Okay, so 216 is actually 36 multiplied by 6. So we can begin by writing this as 36 multiplied by 6, just like that. And 36, of course, is 6 squared. And this now allows us to take the square root of 36 and write it as 6. And this will leave only 6, this one here, left as the radicand. And here's a second example, which is very much the same. The number 162 is 81 times 2. 81, of course, is 9 squared. So here we used 6 squared. Here we have 9 squared. So we write the square root of 81 as 9. And then that will be multiplied by root 2 in our final answer. Okay, this one is similar, number 10, but we now have literal expressions instead of actual numbers. So we're concerned with the exponents. All right, so I'll show you what we're going to do. We're going to write q to the 5 and r cubed differently. So we're going to write q to the 5 like this. Q to the 4 times q. And similarly, r cubed can be written r squared times r. And we did this because q to the 4 and r squared are now perfect square factors. So we can say the square root of q to the 4 will be q squared. And the square root of r squared will be r. So these items here have been dealt with. And underneath this square root sign, now we will only have p, q, and r. And it's important to note here that the exponent here would be 1, the exponent here would be 1. So the two exponents on Q must add to 5. The two exponents on R must add to 3 in that first step. Okay, and then again, it's the square root of Q to the 4 is Q squared. Okay, here is another one, and we'll do much the same thing. Now, for the number 15, of course, there is no perfect square factor of 15. 15 is not divisible by 4 or 9 or 16 and so on. So we can't do anything about that, but we can handle these literal parts. So once again, a cubed, we can write a squared times a. Now b to the 8 is already a perfect square factor. Okay, and that's because 8 is an even number. So we can leave that part alone. We just have to rewrite a cubed. And now we do this. The square root of the a squared portion is a. The square root of b to the 8 is b to the 4. So what will be left under our square root sign? Well, we've dealt with this item and this item already. So only 15a will be left underneath, like that. Okay, here's another one, number 14. Now, we have the square root of 63. Does 63 have any factors that are perfect squares? Yes, because 63 is divisible by 9, and 9 is 3 squared. So we start by writing 63 as 9 times 6. We don't have to rewrite m squared because this exponent is already even. Now, n to the 9, we write it as n to the 8 times n. Okay, so we're taking the largest even exponent here. Again, 8 plus 1 gives us 9. And now we can take the square root of 9, m squared, and n to the 8. So the square root of 9 is 3. The square root of m squared is m. The square root of n to the 8 is n to the 4. So we've now dealt with this, and this. So what's left underneath? 6n. Oh, I completely messed that up though, right? Because 63 is 9 times 7, not 9 times 6. So this is 7. My apologies. So left under our square root sign here is 7n. Sorry about that. Okay, much better. 63 is 9 times 7. So the 7n is left under here. I'm sure you were noting that minutes ago and were wishing that you could tell me, but since it's not a live class, that became a challenge for sure. Okay, now have a look. All of these first examples had an index of 2. Now we're changing the index. So we are now looking not for a perfect square factor. See? We have now an index of 4. So we're looking for perfect fourths. So 48. Well, 2 to the power of 4 is 16. And 48 is 16 times 3. So we should write it as 16 times 3. And then we do this. The fourth root of 16 is 2. So then left as our radical will be the fourth root of 3. Okay, here's another example. We have an index of 3. Okay, now 8 cubed is 512. But we have a negative sign here. In fact, negative 8 cubed is 512. So if it's helpful, we can do that in our first step. We can change negative 512 to the cube of negative 8. And then we're taking the cube root of negative 8 all cubed, so our answer is negative 8. Okay, now take a look at number 20 here. The index is 3, so we can't do anything with the 5 because certainly it's not divisible by 2 cubed or 3 cubed or anything like that. We can't do anything with b squared because its exponent is less than 3. But we can change a to the power of 4. So we should change it to a cubed times a, because then that allows us to do the cubed root of a cubed is a, and then left under the cube root sign, so we've dealt with this part already, will be 5ab squared. Just like that. Okay, the next one here, the index is 5. So again, 16 is certainly not divisible by 2 to the power of 5. 2 to the power of 5 is 32 already. Okay, the x already has an exponent of 5, so that's good. Y has an exponent less than 5, so we cannot do anything with that, but we can rewrite the last term. Okay, so what we should do here is write this as z to the 10 times z, because 10 is the largest multiple of 5 that we can use here. Okay, so again, the exponent 10 plus 1 will give us the 11 here. And now we take the fifth root of x to the 5 and z to the 10. So the fifth root of x to the 5 will be x. The fifth root of z to the 10 will be z squared. And now we will have our radical with an index of 5. Excuse me, we've already dealt with these two items. So left underneath will be 16 and y cubed and z, just like that. Okay, so that's example 22. So let's keep going because there's a really good variety included in our textbook. So we should definitely continue here. So for example, take a look at the next question. We actually have the multiplication here of two radicals with the same index. So what we can do is actually combine these now into one single radical. So what we have to do is multiply 4 by 64, and this will be 256. And now we can check, is there a seventh power that divides into 256? So we should check 2. Okay, so 2 to the 7 is 128. And 256 is 128 times 2. So this means we can now take the seventh root of 128 and make that 2. So then left will be the 7th root of 2. So this is our reduced form. So again, if these have the same index, we can simply multiply the two radicands together like this. Now in here, we do have 2 to the 7 as a factor. Okay, this one, very same thing. The index is 6. So first thing we're gonna do is combine these. So I'm gonna do 3 times 9 and make this 27. And now we're multiplying m to the 5 by m. This becomes m to the 6. The exponents add. We're multiplying n to the 8 by n. So this will become n to the 9, just like this. Okay, now as we did in the previous examples, we take a look. Now there is like 2 to the 6, 3 to the 6. Those are not factors of 27. M to the 6 is already here to be reduced. Let's rewrite n to the 9. So 9 is larger than 6. So we can break this down into n to the 6 times n cubed. So this means in its reduced form now, we will take the 6th root of m to the 6 and n to the 6 right here. Those will be m times n. And then beside it, we will have the 6th root of 27 n cubed. Just like that. Okay, so this is very much like what we've done in many of the previous examples. But now we're going to do something new. It's based on the fact that 27 is 3 cubed. So let's rewrite that. So we have now the 6th root of 3 cubed n cubed. And that is going to allow us to change this radical. And it's the first time we're going to do this, reduce the index of the radical. It's the same as reducing a fraction. See, if we were to change this from radical form to the form with the fractional exponents, the exponents would be 3 over 6, 3 over 6, and 3 over 6 is the same as 1/2. So that means we can change this to a square root, and this would be 3 to the 1, n to the 1. So again, the fraction 3 over 6, 3 over 6, these fractions are now 1/2, 1/2. And finally, I'm going to write that as the square root of 3n. So obviously we can drop these exponents of 1, and even more than that, remember, if no index is written, it is implied to be a 2. So that question is now complete. Okay, now our next one will be the first time we're going to use rationalization of the denominator. So let's have a look. We have 1 over the square root of 2. We would like for there not to be a radical in the denominator. So what we can do is multiply by the square root of 2 over the square root of 2. Why did I choose that? Well, it's equal to 1, first of all, so nothing will be changed in terms of the value. But I picked the square root of 2 because now in the bottom we have the square root of 2 multiplied by the square root of 2. So that will simply be 2. I should start using a ruler maybe, huh? Is this getting too messy? Okay, so once again, in the bottom, we have the square root of 2 times the square root of 2. So it will just be 2. And what do we have on top? We have 1 times the square root of 2. Or root 2. So all we've done is we've changed 1 over root 2 into root 2 over 2. So they're equal to each other. Here's another example, okay? So in this case, we are going to multiply top and bottom by square root 12 over square root 12. Again, it's equal to 1, which is very important. In the bottom now, we have square root 12 times square root 12. So we have 12, which is a rational number. Now in the top, we have to take the product of 11 and 12, and that's 132. Okay, so that's almost perfect, except 132 has 2 squared as a factor. So we should write it as 2 squared multiplied by 33. Like this. We're looking for perfect square factors because the index was 2. And now here we go. We can now reduce that top. The square root of 4 is 2. So we have 2 square root 33 over 12. And lastly, we can reduce 2 over 12. So 2 over 12 is 1 over 6. Okay, but the 1 out front here is not necessary. It would be 1 times root 33. So here is our final result. Okay, now we have to be careful because the index has changed. Now we have an index of 4 here, an index of 4. So it's important to note in this example that that denominator is already 5 squared. Okay, so we have 5 squared already. So when choosing what to multiply top and bottom by, we should pick the 4th root here of 5 squared. Because then we will have in the bottom, you see, the 4th root of 5 to the power of 4. Okay. So that will be in the bottom now, just a 5. But we can show the step first. So let's continue. This will now be the 4th root of, I should make that a little bigger. Okay, so in the bottom, we're going to have 5 to the 4. And in the top, we're going to have 2 times 25 or 50. So here's the whole key. The bottom will now be the rational number 5 because we're taking the 4th root of 5 to the 4. So in the top, we have the 4th root of 50. Okay, and then we have our final answer because 50 does not have any factors that are perfect fourths. Okay, it's not divisible by 2 to the 4 or 3 to the 4, for example. So we know we're done. Okay, this one is similar. So again, take a look. This was already 5 squared. So we only needed 5 squared more here. because the index was 4. So here's another case that's similar. Again, we need to begin by changing the 4 in the bottom to 2 squared. Okay, because now we have already 2. The index is 6. So we know that we are going to multiply top and bottom by 2 to the 4. Okay, so that is going to get us to a denominator of 2 to the power of 6 right here. And the numerator is going to be 16 times 5, or 80. And in the last step, we take the square root of 2 to the 6, giving us 2 as the rational denominator. And we're done. Okay, so those were some examples. These last 4, some examples of rationalizing the denominator. Now, let's have a look at 36. So again, when you see the it's important that you start to recognize these numbers. 81 is 3 to the power of 4. So now, if we think of this, this is the same as 3 to the 4/8. And 3 to the 4/8 is the same as 3 to the half. So you can reduce this to 3 to the half, like that. And then we drop the implied 1 as well as the implied 2, and we end up with square root 3. So we reduced the index, which was the second rule from the beginning of our class. Okay, here's another one. So 27 is 3 cubed. So this is the same as 3 to the 3/9. And 3 to the 3/9 is the same as 3 to the 1/3. So we change 3 over 9 to 1 over 3. We've reduced the fraction, and this leads to a reduced index. So cube root 3 is the answer to 38. Okay, now look, number 40 is interesting because it's in scientific notation, but we can simply just handle each part separately. So the square root of 4 is 2. The square root of 10 to the 6, so it's 10 to the 6 over 2. So we get 10 cubed, just like that. So this one is similar, but look, the index is 3. 16 is not a perfect cube. 10 to the 5 is not a perfect cube, but they have perfect cube factors. 16 is 2 cubed, or 8 times 2. And 10 to the 5 is 10 cubed times 10 squared. Like that. Cube root. Okay, so now we've identified the perfect cube factors of 8 and 10 cubed. Again, check. 3 plus 2 is 5. So now we can do this. The cube root of 8 is 2. And the cube root of 10 cubed is 10. So left under our cube root sign, so we've already handled this, and this will be 2 times 10 squared. Okay, and I guess we could leave it like this because it started in scientific notation. This portion is scientific notation. This portion here, the radicand, is also scientific notation, but it might make more sense to change this to 20 times the cube root of, this is 2 times 100 or 200. So we end up with 20 times the cube root of 200 as our final answer. Okay, now take a look at 44. These numbers are less than 6. Okay, so we cannot use the first rule in any way. Okay, the exponents there are less than the index, but we can reduce the index because we have 2 over 6 and 4 over 6, right? So 2 over 6 is the same as 1/3. 4 over 6 is the same as 2/3. Okay, so again, we had 2 over 6, so that's 1/3. We had 4 over 6, so that is 2/3, like that. So we are able to reduce the index. So in the end, all of these numbers were divided by 2. So final answer is the cube root of BC squared, like that. Okay, so if you recall back here, if we were multiplying radicals with the same index, that could be performed. This one is division of radicals of the same index. So again, we can start by simply taking 320 and dividing it by 5 to get 64. So that is our first step. And now we look at the number 64. Is it divisible by 2 to the 4 or 3 to the 4? Yeah, so it's definitely divisible by 2 to the 4. 2 to the 4 is 16. And 64 is 16 times 4. So now what we can do is take the 4th root of 16, and that's 2. And then beside here, we will have the 4th root of 4. And that's pretty perfect, except we might recall that 4 is 2 squared. So this then becomes the 4th root of 2 squared, and that'll allow us to reduce the index right here. We have 2 over 4, so we can make it 1 over 2. So it becomes the square root of 2 to the 1. And if we drop these implied notations, we end up with our final answer, which is 2 times the square root of 2. Okay, so the key is we can just perform the division here first. Then I found that this number, the radicand, was divisible by 2 to the power of 4. So I reduced first, and then just noticing 4 is 2 squared. So that allows us to change this to a 1 and this to a 2. Okay, I know I'm going through a lot of examples and this is a rather lengthy video, but as I said, they're all so unique, and I think that we really should go through all of them, okay? So you take a break when you need to because it's just a video, but I'm gonna go through this last page here as well. So take a look at what we have here now. We have this radical underneath this 5th root sign. So I just need you to know that in this case, these two numbers multiply together. So this, believe it or not, becomes the 20th root of 9. Okay, now 9, however, is 3 squared. So this allows us to divide both of these numbers by 2. So we end up with the 10th root of 3 as our answer. Okay, now this is similar in that we have this radical under this square root sign. So I'm going to split these just to make it a little more clear. So what we actually have here is the square root of b to the 4 multiplied by the square root of the square root of a. Okay, so what is the square root of b to the 4? So let's handle this part first. Don't forget, a 2 is implied here, right? So it is a square root. And again, a 2 implied here, a 2 implied here. So the square root of b to the 4 is just b squared. And what is that multiplied by? Well, these indices multiply together. So this is now the 4th root of a. Okay, much like 5 times 4 gave us 20 here. Here we do 2 times 2 gives us 4. So that's our final answer, b squared times the 4th root of a. Okay, let's look at this next one. We have a negative exponent. So the first thing we're going to do is rewrite this with y to the 7 as the denominator of that radicand. So 98, x to the 6 will be the numerator. Okay, now maybe at this point we can rationalize the denominator. So that's one of the things we have to do. We could also reduce, okay? But maybe I'll start with rationalizing the denominator. So the index is 2. We have a 7 here. So we want the, basically we want the next even one. So if I just multiply top and bottom by the square root of y, that'll give me y to the 8th in the denominator. Okay, so we're gonna have in our next step y to the 8 down here, which is good because remember the index is 2. So the square root of y to the 8 will be y to the 4. Okay, so now in the top we still of course have 98 x to the 6, and now we have a y up top as well. Okay, so as I said, in our very next step, we can change the bottom. So the bottom will now just be y to the 4. So it's considered rationalized. There's no more square root sign in the bottom. Okay, so that's good. But we certainly can reduce this top radical using our very first rule. So we have an index of 2, so we're going to remove all perfect square factors. All perfect square factors. So focusing on that 98. So what is the largest perfect square factor of 98? Well, it's 49. So 98 is 49 times 2. 49, of course, is 7 squared. X to the 6 is already set because 6 is a multiple of 2. We can't do anything with the y here in the top because its exponent is 1, which is smaller than the index. So here we go. Let's finally reduce that numerator. So we do the square root of 49 is 7, and the square root of x to the 6 is x cubed. So we've now handled this part and this part. So left under our radical symbol will only be 2 and y. Okay, so that one required a lot of steps to get to that final answer. Okay, let's look at 54. We have these two numbers added under the square root sign. The point of this example is just to show you that we can simply add those numbers. So now we have the square root of 90. Does 90 have any perfect square factors? Yes, it does. 3 squared is a factor. 3 squared is 9, and 90 is 9 times 10. So we change 90 into 9 times 10. The square root of 9 is 3. So we end up with 3 times the square root of 10. Okay, let's take a look at 56. The index is 2. In the bottom, we have m cubed. If we want to rationalize the denominator, we just need to multiply by one more m down there, because then we'll have the square root of m to the 4. And the square root of m to the 4, of course, is m squared. Okay, so this is equal to 1, since top and bottom here are the same. So let's go. This now is going to have in the denominator m to the 4. And in the numerator, m times n. We usually just go alphabetical order, but you could write n times m instead. It's the same thing. Okay, so again, the key is the denominator now is the square root of m to the 4. The square root of m to the 4 is m squared. The numerator will remain the square root of mn. So that was an example of rationalizing the denominator. Okay, so just like in number 54, we would like to add these two things together. But they're fractional, which means we require a common denominator. So the common denominator will have to be the product of a squared and b. All right, so if I change this denominator to a squared b, then the numerator, of course, will be b. And if I change this denominator also to a squared b, then the numerator will be a squared. So this allows us to combine this now. The denominator is now common. The numerator will be b plus a squared, or a squared plus b, like that. Okay, so that looks pretty good, except if I want to rationalize the denominator, this part's already set for that. But we have b to the 1. We need it to be b to the 2 since the index is 2. So we multiply top and bottom here by square root b. Okay, so let's see what that's going to look like. Okay, so the bottom will now be a squared times b squared under here. And the top will be b multiplied by a squared plus b. Just like that. So now at the bottom, we take the square root of a squared b squared, giving us just ab. And the top, of course, will still have a square root sign, like that. So we're finally done. So we had to get a common denominator for the fractions. And once we had a common denominator, we took a look at that denominator and noticed that in order to rationalize, we needed multiplication by b over b. Okay, problem 60. So the first thing we'll do is take 4 to the negative 1 and change it to a quarter. So this is now x squared plus 1/4. Now, again, if we actually want to add here, x squared, which is currently over 1, needs a denominator of 4. So we can change it to 4x squared over 4. So we now have 4x squared over 4 plus 1/4. We can combine the fractions now like this. And finally, in the bottom, the square root of 4 is 2. So we will have 2. And the numerator is the square root of 4x squared plus 1. And this is a binomial. And it is not a perfect square. We have to leave it just like this. Okay, which is different from our next example. We have a trinomial. The factored form of that trinomial is a plus b all squared. Okay, so I'm hoping you can recognize that. However, at the very least, you should be able to check it. You could take a plus b, right? And multiply it by a plus b. You'll see that, in fact, you will get back this trinomial. You'd go first, outside, inside, last. Collect the like terms there in the middle. Okay, so the original trinomial that was here and its factored version. Okay, so now of course we have the square root of this perfect square. This is simply a plus b as the final answer. Okay, take a look at 64. What's the factored version of that binomial? In fact, if we were going to factor it, we would not get a perfect square, okay? This is difference of squares, right? Note the sign. 2x plus 1, 2x minus 1 is the factored version of this binomial. So these factors are different from each other. So we don't have a perfect square like we did in 62. So we just have to leave our answer like that. Okay, one last example. So number 66, take a look. We're gonna make these have a denominator of 2 also, so that we can actually combine these things. So if we did that, I'm going to change the order as well. Right now, these guys have denominators of 1, of course. So if we change their denominators to 2, this would be 4r over 2 and 4r squared over 2. So I'm going to write them in this order. All right. And now that the denominators are all the same, of course, that's going to allow us to write them in this way with a single denominator. Okay, now this trinomial can be factored, and it certainly is a perfect square. It is 2r plus 1 all squared. Okay, so again, hopefully you can do that factoring, no problem. I know you had a full lesson, rather a full unit on factoring. At the very least, once again, you should be able to expand 2r plus 1 all squared to see that it is indeed equal to this trinomial. But more importantly, you do need to be able to go from this version to this factored version here. And what does this allow us to do? Well, in the top then, we have the square root of 2r plus 1 all squared. So that's just 2r plus 1. But in the bottom right now, we would still have the square root of 2, like this. So we have to finish by rationalizing the denominator. We multiply both top and bottom by the square root of 2. This means that our denominator will now be 2. And in the numerator, we will have the square root of 2 multiplied by 2r plus 1. Just like that. And now we're finally finished. Okay, so we have just completed all of the relevant even numbered problems from exercises 11.3 of your textbook. Again, the topic was simplest radical form. It involved 3 parts. You have to make sure that all perfect nth power factors have been removed. You need to reduce the index where possible, and you must also make sure you rationalize the denominator where applicable. So it would be great if you now tried the odd numbered problems. Okay, so again, this is exercises 11.3 from your textbook. When you're trying the odd numbered problems, of course, you'll be able to check your answers, which are at the back of your textbooks. Okay, thanks so much for watching. Work hard, and don't forget that I welcome your questions either through email or in person during our classes. Okay, thank you. Have a great day.